Direct to print aligners. Will they change clear aligner therapy? Welcome to this episode of Orthodontics in Summary, where we take a dive into direct to print aligners. This material's been around in the market since 2019, and we looked at this topic 2 years ago. Today we're going to update what we know about direct to print aligners. We'll go through some of the claims offered by the manufacturers. We'll also dive into what the advantages are looking like in terms of current studies, and perhaps why this material hasn't yet changed clear aligner therapy. This podcast is based on a lecture given by Jean-Marc Retrouvey, one of our previous guests on the Orthodontics in Interview podcast. Now, to describe what direct-to-print aligners are, well, they are, simply put, a resin material, a photopolymer version of them, and that's significantly different to conventional clear aligner therapy, thermoplastic polymer. Now, the key distinction between these two materials really relates to the force delivery, and that's what we'll explore in this podcast, looking at the push and pull possible with direct-to-print aligners, the adaptability to the surface, and what other material properties are offered. One of the key claims relates to the ability to reactivate the material, the idea of being able to heat the material and restoring the force properties of it. Therefore, the claims that are made around direct-to-print aligners is that they do not require attachments or require less attachments. The other claim relates to the manufacturing of it. It's much quicker. There is no requirement to print a resin model followed by the thermoforming process. Actually, it's a one-stage process of printing, and therefore an aligner can be created within 1 to 2 hours, significantly shorter than the conventional thermoforming process. The other advantage is that there's less wastage from an environmental perspective. Let's jump into looking at force delivery through push and pull of direct-to-print aligners. Now, I'll compare this to conventional thermoplastic aligners, where they are not able to engage in the undercut surface of a tooth, depending on the direction of movement. And it means that a significant amount of the aligner is not delivering the force. That is different when it comes to direct-to-print aligners. A study by Hurton in 2022 showed that direct-to-print aligners will engage with the undercut surfaces of teeth. How is that possible? Well, that relates to the second quality of direct-to-print aligners, the adaptation. The idea that they are closer to the tooth surface by 20 to 30% compared to conventional thermoplastic aligners. And that's 30 microns of difference. That's from Koenig's study. And they looked at a range of different conventional thermoplastic aligners, Zendura, Essex Ace, and direct-to-print aligners came up on top. They also have a uniform thickness, something which conventional thermoplastic aligners struggle with. Due to the nature of the fabrication, it results in the ends of the aligner being thinner. In a uniform surface, it results in a broader distribution of forces and therefore greater control when it comes to delivering those forces. With conventional aligners, there's always a sharp distribution, generally around attachments and transition surfaces that are present. The material itself, well, actually both conventional thermoplastic aligners and direct-to-print aligners suffer from stress relaxation. Well, what is that? It's a change in the tooth surface that takes place with time, which results in a significant reduction of the force delivery. Now, conventional aligners, thermoplastic aligners, reduced by 60%. Direct-to-print aligners are very close to that, at 50% reduction at 12 hours. The key distinction here is that ability to reactivate or recover the material properties through heating it, whether it's using water in terms of LuxCreo, which is 60 degrees, or in the patient's mouth in terms of Graphy, both able to recover the material properties. Now, that makes a significant impact in terms of our biomechanics. The challenge with conventional thermoplastic aligners is that we may actually have the ideal moment to force ratio to control both the body of the tooth, but also the root position as well. But as there is stress relaxation which occurs, it results in a change in this moment to force ratio, favouring tipping over bodily movement. Now, although direct-to-print aligners also undergo this loss of force, it is recovered, enabling a better to moment to force ratio. Now, at the moment, the in vitro studies support body movement taking place with direct-to-print aligners over conventional thermoformed aligners. What other features are there? Well, we can select different trim lines, but there's also the ability to change and customize the thickness of the aligner. And I think this is probably the most exciting bit in terms of biomechanics, because you can create a force couple within the aligner itself, simply by having a thicker labial face relative to the lingual face, we can control the root movement which is taking place. In terms of materials available in the market, there are two main players: Graphy, which claims to be a shape memory aligner, and LuxCreo, which claims to be an active memory aligner. So I looked into these two materials because in terminology sense, they sound quite confusing and similar. But actually, most of the claims made between these two materials are essentially the same. The ability to reactivate the material or restore its material properties through heating, to customize the thickness, to have less attachments or no attachments, the speed of printing and less wastage. Actually, the only difference I could really find was related to the transition temperature. So bear with me, there's a technical component to this. In terms of shape memory or Graphy aligners, the transition temperature is lower, around 45 degrees. And as the material approximates this temperature, it starts to change its properties. What does that mean in clinical practice? Well, it gets placed in the patient's mouth, the material heats up, the forces are reduced, which means it undergoes a more likely delivery of a continuous light force. Think of it similar to a thermally activated nickel titanium wire. In the other direction, in this case of the direct to print aligner, the temperature increases. As temperature increases, the force reduces, but it gives that light continuous force. In terms of active memory or LuxCreo aligners, they came later to the market in 2022. Now, the difference here is that the thermal transition temperature is much higher at around 60 degrees. Well, what does that mean? It means it maintains its material properties when it's inside the patient's mouth, giving us potentially that higher moment to force ratio. So why haven't direct to print aligners changed the landscape of clear aligner therapy? Well, the first is the most obvious: the lack of clinical research. What I described to you so far has been mainly in vitro studies, and the ideas and concepts sound very much appealing to the biomechanists amongst us. However, we need to see that happen in terms of clinical research. The loss of force still takes place with the use of direct-to-print aligners. Although we may recover the forces, in that interim we will get a change to the moment-to-force ratio. I think that's where the challenge still lies in terms of clear aligner therapy. Can we sustain the ideal moment-to-force ratio in terms of tooth movement? Effectiveness. Is it any better? Well, we've mentioned there's no direct studies comparing the two. However, there was a clinical study last year which looked at direct-to-print aligners and showed it was clinically effective for mild to moderate cases. And that was Canode's study from 2025. However, the refinement rate was 40%. Now, when we compare those rates to thermoplastic aligners, in terms of the clinical effectiveness, they seem to be similar at approximately 89%. And that was Jarber's study from back in 2022. Yes, the refinement rates seem to be higher for conventional thermoplastic aligners, but we're still yet to see, are these material properties enabling us to achieve better clinical results in terms of clear aligner therapy? Overall, I think this material has a lot of ideas and premises and ability in terms of what it could deliver. We really now need to see our academics and universities coming on board to investigate these claims and to see, can this be something which changes how we clinically practice? As always, please do subscribe and look forward to the next episode.